In this video, we are going to look at a undecidable problem that has nothing to do with any man-made devices. So the undecidable problems we have looked at so far, they are all related to certain types of languages. For instance, we asked several questions about regular languages, about context-free languages, about halting problems, about acceptance. So all of those languages really depend on man-made devices, right? So we know that we have these context-free grammars, push-down automata, finite automata, and Turing machines. So they don't seem natural. They are not natural, not just don't seem natural. They are not natural problems in the sense that they depend on machines. They depend on certain things that humans made. Well, in other words, computing devices. So today we are going to look at the first problem. Historically, it was the first problem, which is quote-unquote natural, that was proven to be undecidable or unsolvable. And this problem is called post-correspondence problem. Okay. Now let's look at what this problem talks about. So we suppose we have a collection of dominoes, and these dominoes contain, each of these dominoes contain two strings, one on top or one at the bottom. So normally dominoes is like this. You divide it into two halves, right? So if you look at the domino, they may have some dots. So that is one domino, right? And then the other one would be a different pattern. So instead of using dots, we are going to use strings over a finite alphabet to represent the top and the bottom. Okay, so for instance, so we have an instance of a collection of dominoes. So we have 4 dominoes in this set. Okay, so this is the top symbol is B, the bottom symbol is CA, so this is one domino. The other one is A, and then the top is A, the bottom is AB, and the third, the top is CA, the bottom is A, and the fourth, the top is ABC, and the bottom is C. So these 4 dominoes are given. So our task is to make a list of these dominoes. We can reuse a domino in any way we want, so that the strings we get by reading off the symbols on the top is exactly the same as the string of symbols on the bottom. Okay, so then if such dominoes exist, then we call it a match. For instance, for the given 4 dominoes, we have the following match. So if we put this domino 1, 2, 3, 4. So the match will be, we use the second domino, and then the fourth domino, sorry, the second and the third. The second, the first, and the third, the second, and the fourth. So this is a list of dominoes, and then what we are getting, so this is 2, this is 1, this is 3, this is 2, this is 4. So if you read off on top, you have a string A, B, C, A, B, C. And if you read off the symbols at the bottom, you will also get A, B, C, A, B, C. So they are a match, okay? So they match each other. And this is what we are looking for any given collection of dominoes. We want to know whether there is a match. Okay. So now we described PCP problem, post-correspondence problem. Oh, by the way, this problem was first published by Post. Okay, so he was a mathematician, and he made a substantial contribution to the study of recursion theory, which is the study of computability at a very abstract level. Okay. So now, so let's look at this input. So let's look at the description of this problem. So the input is a collection of dominoes. Sometimes we call it an instance. So this is also called an instance of a given problem. So let's say we have K dominoes, and each of these domino on top, you have a string T1 for the first one. The bottom is a string B1. The second on top is T1. At the bottom is B2, and so on. So what we want to know is that for this given instance, whether there is a match. In other words, whether we can find a sequence I1, I2 up to IL. Now remember, a domino could be used more than once. Okay, so then we have a sequence just like in the previous example, we have a sequence 2, 1, 3, 2, 4. So that is a sequence for that particular instance to generate a match. So now we just want to know whether there is a sequence such that you read off the symbols on top. Okay, so that will be TI1, TI2 up to TIL, and that string is the same as the symbol you read off at the bottom, which is BI1, BI2, BIL. Okay, so that is what we want to know. So then we want to make it a decidable problem. So we put the encoding under a fixed encoding method, for instance, using ASCII. So in encoding key of any instance of collection of dominoes, which is the element of the set, such that P has a match. Okay, so that we make it to a decidable problem. So what we really want to know is for a given instance of PCP, so a collection of dominoes, we want to know whether this is in PCP. So that now it is a decidable. So this is a decidable problem. Sorry, this is a decision problem, not decidable. Okay. When a problem is decidable, it means that you have a decider that answers this question. So right now we don't know whether this question can be answered by a decider. As a matter of fact, we're going to show that this is not decidable. Okay, so this decision problem is unsolvable. So that's what it is. Okay, so the theorem is simple. It just says that PCP is undecidable. And now we're going to see how we can prove this theorem. So first, for simplicity, we consider a restricted PCP. So in other words, we modify PCP a little bit just to make things easier. And later on, we are going to look at a general case. So this modified PCP, denoted by MPCP, is a collection of encoding of instances of PCP, encoding of a collection of dominoes where it has a match, and the match starts with the first domino. So in other words, I1 is always equal to 1. So so such a match always begins with the first domino. Okay, so this is called a modified PCP. All right. So what we are going to do is to prove this MPCP is undecidable. And the way to do so is to reduce A sub Tm to MPCP. So again, A sub Tm, to refresh our mind. So A sub Tm is a set of encodings of a Turing machine M and an input to M, such that M is a Turing machine and accepts X. Okay, so we know that A sub Tm is undecidable, and we prove it using direct diagonalization. Okay, so that is the, so the roadmap for this to study unsolvability is that we first use diagonalization to prove the first undecidable problem. So this is the first undecidable problem. So once we have one undecidable problem proven, then we can use it to prove other problems to be undecidable by reducing it, okay, to the other problem. Okay, so that's what we are doing here. So we're going to reduce A sub Tm to MPCP, meaning that we have to construct a Turing machine. All right, so now we construct a Turing machine that turns an input, or this is an instance, let me just call it an instance. So this will be an instance, which is encoding of M comma X to a collection of an instance of PCP. Then we're going to call it P sub M comma X, because this instance depends on this instance M comma X. So it depends on it. So there's a subscript M comma X indicates that this instance of dominoes depend on this instance of A sub Tm, which is a Turing machine and an input X. Of course, now we're going to try to use dominoes to describe the computation history of M on input X. Okay, so this is domino is going to be used to simulate the computation of MX, and such that, okay, so this is important because that's what the reduction is, okay, such that M accepts X if and only if this collection of dominoes, or this instance of PCP, this encoding, okay, is in MPCP. So again, remember this MPCP means that it always begins with the first domino in P sub M comma X. Okay. As I said earlier, so the idea of doing this, or the idea of constructing this reduction is to come up with a set of dominoes such that we can use this set of dominoes to simulate or replicate a computation history, okay, or the computation history of M. So this is the computation history of M on input X. Okay, so that's what we are going to do, and you may assume that this M is deterministic. Okay, so when we don't say anything, it's deterministic. You can always assume that as deterministic because for Turing machines, deterministic Turing machine has the same power in terms of computability of non-deterministic Turing machines. Okay, so you can always assume that it's deterministic. So then the construction of this dominoes obviously will depend on X. Okay, so that's the first thing. The second, of course, it depends on the transition function of M, because the description of M is really about its transition. But then in order to describe this transition function, we have to look at the number of states, the tape symbols. Okay, so that's what we are going to look at. So we have Q gamma. So that we need to look at, because this transition, the description of the transition needs Q, needs gamma. So then we have a Q, we have a gamma. Now this gamma is a set of symbols that we use on the tape. So that gamma includes sigma. And to make it easier, we assume that delta, this transition delta, does not attempt to move out of the left-hand boundary of the tape. Okay, so this is, so we have a one-sided tape. So this is going on, that you have a left boundary. So and this transition, when it's at the boundary, it does not attempt to move out. Does not attempt to move out of the boundary. So which is easy to make it happen. So we can, if it does, we can always construct a new transition that will not do it. Okay, so we can just say, if you want to do it at the new transition, just say, okay, it remains. All right, so now let's see how we can use a set of dominoes to represent or replicate a computation history. Okay, so once again, we would like to look at what is needed to look at a computation history. Okay, so this is to begin with, we are going to have an initial configuration so that you have an input X. Say this is X. And at the beginning is Q. So it starts at an initial state. So initial state points at the left symbol of X, the leftmost symbol of X. And in order to indicate this X is what we are going to look at. So in our domino, we are going to put a pound sign at the left-hand side, indicates this is the left boundary. So we have the configuration Q0X. So that's the bottom because that's where we begin with. And then, of course, if you do one move, then you can go to the next configuration. So that would be the next configuration. So we want a match, which is the bottom on top. So that means I can put the next configuration on top of it, on top of this. Okay, so that probably would help you to think how we can use dominoes to replicate computation histories. And of course, depending on the transition you move, then of course the next one will be on top of this. Okay, so this match is always the bottom, match the top. So then when you are here, the top for the first one becomes the bottom, and that will match the top, and so on. So you can see here in this particular initial case, so we begin with a pound sign, and this is the initial configuration. And X here could be empty string. So when that happens, we use this particular symbol to indicate it is an empty string to begin with. So there's a pound sign. On top of it is a pound sign because the match, okay, on top should depend on the transition, which is going to be represented using new dominoes. Okay, so now let's look at these dominoes. Okay, now we're going to look at how we're going to use dominoes to replicate transition function or to represent transition function. So of course we have transition could be either, let's say you're on a current state Q. Okay, you have input A, and then you rewrite A to B. You move from Q to R, and then you move to the right, or you can move to the left. Okay, so these are two transitions we are dealing with. And here we assume that this Q is not QR. Okay, it's not a rejecting holding, but it could be a accepting holding. We can. Okay, so if this is the case, so that means now if it's on bottom, we actually, so this is a the top is QA, so this is top is what we are reading, and the bottom is the result that we move to. Okay, so that means on top of it indicates this is like Q, and it points at A, and then you move to the right, change A to B. Okay, so A becomes a B, and R now, your re has moved, so then that's R. Okay, so then I want to rewrite this as a domino, so then I'm going to put QA on top and BR at the bottom. All right. Okay. So this is to replicate. This is the idea of doing so is to use dominoes to replicate a computation history. Okay, so that so this is basically what it looks like. So the computation, for instance, you begin with your. Remember, we begin with Q 0x, let's say Q0 on the first symbol, you are going to change it. So for instance, we can think of this x as let's just assume Q0 is Q, and the symbol here is A, and then this is X2, so X1 is A, Xn. So remember, that's where we begin with for that domino, and then on top of it is pound sign. Okay, and then Q0, let's say on A, so the next one then it goes to, so this one then goes to so this Q0 on A becomes, let's say it goes to, rewrite A to B, goes to R, okay? And then what we're going to have on top of it is Q, so you move this up, Q0A. So now you can see I have a partial matching of this one. Okay, so then depending on R, what you're gonna do, and you're gonna extend it, and then you get another partial matching because you're going to put A on top. So A is already on top, but this X2 is where, so you're going to read it here, and then you're going to do a match that way. Okay, so so now you have some idea why we constructed a domino in this way. So of course, the next one would be you try to move to the left. So in this case now, since to the left, we are going to use, let's say I have C, this is a symbol, I have an A, now it's pointed at A, and this is Q, so we move to the left. Let's say we rewrite A to B, so that becomes, A becomes a B, and then this Q now moves to the left. So we put C at the left of B indicates that this is not a boundary. This is not a left boundary, so we can move. If there isn't C here, then we cannot move to the left. Okay, so that's the assumption. It doesn't try to move left of the boundary. So how do we represent? It is not a boundary. That means that I have a symbol on the left of A, which is pointed at the current moment. So then, so to represent this configuration, the part, okay, this is the local part of configuration. So there is a CQA. So we put it on top, and then the configuration, the local configuration it moves to is, oh, sorry, this is not Q, this is R. Okay, so that's RCB. So we made this another domino to replicate this computation step. So this is the transition, and then we are going to, for the rest of it, we are going to say we can always replicate a symbol. So this is a symbol, whatever symbol it is, we can move it up. And for the pound sign, we put this, and also, so this pound sign is a special symbol that is not in the alphabet. And then for the empty thing, in front of the pound sign, we also, on top of it, it's pound. So we'll see why we need this when we actually look at a computation history. So remember here, we say that Q is not QR, but Q could be, well, actually, we can just say that Q is not a halting. So Q is not QR, Q is not a accept halting either. So when it is, we're going to replicate this up. So which means that if we see a QA, then for any symbol A, we can put A, QA on top, to the left of QA or to the right of QA. So that just means that I can fill in the blank when we try to make a match. Okay, so finally, we can also put this pound sign and make 2 pound sign on top now. So these may become a little bit subtle, but when we look at the actual matching later, okay, then we'll see why we need these dominoes in order to make a match. Okay, so we'll come back to this. All right, so now let's look at an example to help us understand how we can use dominoes that we constructed earlier to replicate a computation history. So in this case, we assume our tape alphabet is 0, 1, 2, and space. The input X is 0, 1, 0, 0. And let's look at just one transition step. So Q0 on 0, move to Q7, change 0 to 2, and move it to the right. Okay, so that's the beginning, right? So that means, remember that we have the first domino. So this is the first domino. So this is the first domino. Remember, the first domino is a pound sign on top. The bottom is a pound sign Q0X. But then this X is 0, 1, 0, 0. And also have a pound sign here. So this would be, okay, Q0, 0, 1, 0, 0. So this piece is the first domino. Okay, so let me remove this shaded thing. It's the first domino. Can use red. So this is the first domino. That's what this is. Okay, so we write it as we do a left flush. So we get pound sign on top. And then we get Q0, 0, 1, 0, 0 pound sign. So then this looks like this. That's my first domino. And for this, we know the domino is Q0, 0 on top. And then we change 0 to 2 and move the right head to the right. So we get 2Q7. So that's the next domino. So we get Q0, 0, 2, Q7. So we are going to put it here. So that is 2 Q7, and we got Q0 and 0. So as you can see, here now, up to here, oops, not the one, not including the 1. Okay, up to here, we have a partial matching. So let's do one more thing so you can see how it goes. So the next one, let's say, so the next, we can say we got to replicate. So this is one step. So then we replicate this 1 to top. So let me put this. So we have room. So we replicate 1 up because we have this A. So we have this dominoes. So now we replicate 1 here. That's another. And so that means I get 1. Okay, so this is another one. And then we use 0. So we got 0. We got 0. So that's what we have. So there's a 1 and 1. So this is the second. And this is using 1, 1. Using 0, 0. Using 0, 0, repeat again. And then using pound, pound. So as you can see now, up to this point, we have a partial matching of the initial configuration. Then this starts at the next configuration. So this would be, so this is a new, right? So this is a new configuration. So this is the initial configuration. And with a pound sign, we think about that pound sign. So we can share that pound sign. And this would be the second configuration. So now let's assume that, so let me erase this. Let's assume the next transition is going to the left. Okay, so let's say we have delta. Let's move to blue. So we got, let's say now we have Q7, 1 going to, let's say we change 1 to 0 and move it to Q1, let's say, change 1 to 0 and move it to the left. So remember, for this, we have a domino. On the top is, now remember, we have a 2 on the left, so we got 2, Q7, 1. And the bottom is that we are going to move to the left, so that means Q7, so change to Q1. And 1 becomes 0. And now Q1 points to 2. So that is a domino that we have. So now we are going to put the next configuration. So this is going to be like this. So what we are having here is that Q1. We have this Q1, 2, 0. And then we have 2, Q7, 1 on top. So this is a new domino. So as you can see here, we now have this partial matching. And then 0. So after this transition, everything just replicates. So 0, 0. We got, so let me remove this. Right, it's a fun, right? So it's just like a playing domino game in a new way, right? So then this is another domino, and then there's a 0, 0, and then will be the pound sign. Just repeats. So now, as you can see, depending on the transition, then we can replicate. So now we can keep doing this replication by simulating computation of m on x. So then at some point, okay, so here is what the book gives. The next move also move to the right. So what I did earlier is I will move to the left because I thought that I should provide an example how it goes to the left. So for this, it's a similar, but it could go to the right, could go to the left. So what I show is suppose the next one going to the left. The book says the next one is also going to the right, so you'll end up in this situation. The idea, of course, is similar. It really depends on what the next transition is. It's deterministic, so there is only one. So either, so the book gives us this one, but what I did is just trying to give you an idea what happened. It moves to the left. So after this, we come to a, let's say we come to a halting state, and which is accepting because we assume that the book actually gives you to the left. So let's also move back. Okay, we do this. Okay, so we follow it. So this, as we said, up to this point, the initial configuration is matched. And the next one is that Q7 on 1, change 1 to 0 and going to the right. So that means we are going to have 2, now remember this is going to the right. Q7 on 1, oops. Q7 on 1 on top, the bottom, we change Q7 to Q5 and 1 to 0. So, but before we do this, because it points to 1, so we are going to replicate 2. Okay, so this is another domino. And then we're going to put 0, Q5. So this is transition. And this is Q7, 1. So that is another domino. Okay, so that's where we are at. And then the rest of it, we just duplicate. And another 0. And a pound sign. And then we are ready for the next move. So that's where we are. So the next move, okay, is Q5 on 0, change 0 to 2, Q5 to Q9, and move to the left. Okay, so this is where we are. So this is where we are, where we were from the previous slide. So now we have 0, Q5, 0. Now because it's moved to the left, you have to look at its left hand symbol. And then it changes 0 to 2. So this 0 becomes 2. And then it goes to Q9. So that's Q902, 0, Q50. So now, once again, I'm going to replicate 2. Okay, so we're going to put replicate 2 here. And then put Q902 and 0Q50. So that's another. So this is 1. This is another domino. So this is another, and then put the pound sign up. Okay, so then it's ready for the next move. Okay, so this is one move at a time. So you can see we always have a partial matching, and then assume now a certain, after the few steps, I reach a accepting state. So this is Q accept now, it's reached. And that what we are having is that for this one, we have this particular, now remember from here means that so far I have a match. Okay, so far I have a match. But then how do I match this thing? Right, so we have to fill in this blank. Okay, so that's, now let's see how we're going to fill it in. Okay, so now this is a match. I have up to this 9, it's a match, but I need to fill in for this. So now 2, of course, I replicate up. 1, I replicate, right? So now remember, this is what it's being matched. I have this thing on top. I need to fill. So then 2, I replicate. So 1, I replicate, and then accept here. Remember, I have this QA. For any symbol, you can put it on the left. Do I use A here? So this is QA. So now let's move back to see our, yeah. So A either on the left or on the right. Okay. So now we use on the right. Okay. So that means QA here, I have a QA 0 because I have a 0. So what we need to do is just to construct this matching. Okay. It exists, right? So then 2 just replicate up, pound sign replicate up. So now you can see here that I have used, so the scale is now, this is more than 1 here. So then at least now I have a matching to this point. So I keep doing this, right? So I keep doing this, so get 2 will match and 1 will match. I have 2 and 1, and Q accept will just, so just Q accept, and then on top of it, it'll be Q accept 2. So that's another, okay? And then you keep on doing it until you will have no, so you will have nothing on the right, because that's, you see here, so we got 0 now. So this 0 will be match in here, and then this 2 then will be match here. So then after this QA will become this, okay? But we still have this to fill, okay? So there's still, so we still need to fill that in. So what it does is that we are going to use a new so remember we have this pound. It's a very special one. We say QA double pound. That's why we need to put it here to fill in this blank. So we put this, then it's completely matched. So that means if M accepts X, then we have then we can compute. Then we, so this the dominoes we constructed for that instance, there will be a sequence so that we have a complete match. Now, if M doesn't accept X, so it will either keep on doing, okay, because it may not even hold. So that means the Q accept doesn't, Q accept is not reached. Then of course you always keep on doing, so you don't have a match. It's just only a partial match. You just keep on doing it. Or if it comes to a halting state but rejects, now remember for this QR, we don't have anything like this to fill up the blank on top, okay? So for QR, you don't have it. For Q reject, you don't have it. So then you don't have, so if M doesn't accept X, either it's infinite loop or it rejects X, then you will not have a complete match. So only partial match you can get. All right. So now again, so let me just repeat what I said. So know that only when Q accept is reached, a complete match can be made. Hence, we really have that M accepts X if and only if this instance of MPCP we constructed has a sequence that represents a match of the that has a match and that actually replicates the computation history of M on input X. So that means that this the instance of MPCP we constructed really has a match, so hence it is in MPCP. So that is the first part. So now we are going to reduce MPCP to PCP by making sure any match there is, it must begin with the first domino. But then it is just playing some tricks on the strings. So this is how we are going to do this. So what we are going to do is let, okay, this is your U which is U1, U2, UN, at your current, at the tape, at the moment, right? So this is a tape where UI is a symbol in gamma, right? So in the previous example, it's a 1, 2, 3 and blank. So now we are going to put a special symbol, star. So star U, so star U, so star on the left, okay, U will be put this star sign in front of each symbol. And then U star will be a star sign after each symbol. And then star U star will be, we have is a star before and after each symbol. Okay, so that's what we are going to get. So now, let's say we have an instance of MPCP. Okay, so that's any instance. So it begins T1, B1. So this is the first domino. This is the second. So this is the first. So any match must begin with T1, B1. Okay, so the so this is we are going to reduce this to PCP. So which means now we are going to construct a Turing machine that converts this into a new instance of PCP. So what we are going to add here is on top of it, we're going to put this start on the left of each symbol. So we're going to have star T1 at the bottom is a star B1 star. So we do this twice. So then B1 star. So we got star T1. So on top of it, the star sign is always on the left, but the bottom after this will be on the right, except the last one. The last one we have to do a perfect match. So we have to say this is blank. On top of it will be matched with a star blank. So as you can see here, in order to have a match, now remember, you cannot begin with this. So none of these can be used at the beginning symbol because they don't match. So this star sign doesn't match with B1, star sign doesn't match with B2. So they don't match. So only this one is matched. Okay, so because this is star with this. So that means that for any matching, it must begin with this first one. So that's how we reduce MPCP to PCP. So after this, now we know that we can reduce A sub Tm to PCP. Because A sub Tm is not decidable, so PCP is not decidable. So that's the end of this proof. And the end of this video.